Well, hello everybody. So, we continue without much waste of time. I would again welcome you, and we continue with our discussions on the effect of operating parameters. We were actually discussing the effect of channel inclination. We have already discussed, and I have told you that, well, channel the effect of channel inclination, it's although it's counterintuitive, it is same for your circular tubes, your for other concentric for geometries, including a concentric annulus, a rectangle, a square, etc. But I just wanted to mention one interesting thing which again we had observed in our multi-phase flow laboratory regarding a rectangular conduit. Now, you just see, if you take up a rectangular conduit, the conduit suppose it is horizontal, okay, and we start inclining it. We can incline it either in this particular way, or we can make the conduit like this and we can incline it in this particular way. Normally it should hardly matter, okay, no matter whether we are inclining it along an axis which is passing through the narrow face or along an axis which is passing through the wider face. Normally it should not matter much. For larger channels it did not matter, but when we performed the experiments in a 4 millimeter into 2 millimeter size conduits, and when we were performing experiments, we found something very interesting. Okay, what we found is, we were trying to measure the rise velocities. What we found is that for this particular orientation, for this particular orientation, when it was rising, we found that the nature of variation of the rise velocity with angle of inclination was as expected. The inclination angle, it gradually, the rise velocity, it gradually began to rise from the horizontal orientation. It attained a maximum somewhere between 40 to 50 or something, and then it started decreasing again, just like the typical curve which we observe for liquid Taylor bubbles in circular tubes, gas Taylor bubbles in circular tube, as well as your even for liquid drops. This liquid drops I did not mention, I will not be going into the details of it, we do not have so much time. We find that for liquid systems, when a lighter liquid rises through a heavier liquid, it is known as a liquid Taylor bubble. Same way, if a heavier liquid is made to fall through a lighter liquid, it also assumes the same Taylor bubble sort of a axisymmetric bullet shaped and falls down, and we have named it as a Taylor drop. They too, in Taylor drops also, just to mention, they exhibit the same type of characteristics as liquid Taylor bubbles or jet Taylor bubbles. Their velocity also increases from the horizontal orientation, attains a maximum around 40 to 55 within this particular angle of inclination, and then it decreases again. There also we find that the wake region is much less, but the bubbles are less stable and they tend to break up faster than the liquid Taylor bubbles. Well, to come back to our discussion, so we find that for the first orientation, which is the orientation shown here, we see that the bubble rise velocity, it exhibits the same type of curve as is expected. But if suppose the Taylor bubble is held in this particular way and it is made to rise in this particular fashion, we find firstly that the rise velocity is always less than the other orientation. Number one. The number two, we find that in this case the velocity rises steadily from the horizontal to the vertical orientation, and the rate of rise is faster initially and then it gradually becomes much slower. And obviously this goes beyond saying that the rise velocities in both the orientations are the same for the perfectly vertical and the perfectly horizontal orientation. That is quite expected. So therefore, naturally we wanted to investigate the primary reason for it, and in order to understand the reason, what we did, we tried to observe the shape of the bubble, because we knew one thing from all our experiences on Taylor bubbles rising through liquid filled conduits. One thing we knew, that the rise velocity, it is governed by the shape of the nose. Once the nose is formed, we know that the nose is invariant of no matter how the volume of the bubble or how long the bubble is, the nose once formed is a function of the channel dimension. So in a particular conduit, if the geometry and the dimensions are unchanged, the rise velocity of a Taylor bubble remains unchanged. This is something which we should be remembering as students of multiphase flow. So therefore, we naturally, it came to our mind that definitely it is the shape of the nose which should be different in the two cases, and we found that our supposition is correct, as we see from this particular slide. I think a better view will be this. Here if we see in the horizontal case, we find that the bubble, it is completely asymmetric and completely irregular in this particular case. Now, as we start increasing the inclination, what do we find? We find that the bubble, it gradually starts becoming pointed. It becomes more pointed in this particular case. And gradually, as we keep on increasing the inclination, what we find, that when we attain the vertical orientation, again the bubble has attained the bullet shaped as axisymmetric shape with a rounded nose and a flat body. So therefore, we find that the change in shape in this particular case is as we had expected for, or rather as we had found for Taylor bubbles or kerosene Taylor bubbles in the previous case. And therefore, since the change of shape was as anticipated, the rise velocity curve with inclination was also as expected. On the other hand, when we observed the bubble shape in the second orientation, let me tell you that for both the orientation, the photographs had been taken from the broader face. Quite naturally, the photograph had been taken from here. So naturally, for this particular orientation, the photograph was taken from the top, and for this particular orientation, the photograph was taken from the side, and for the other orientation, the photograph was taken from the top. In this case, we observed that the bubble shape remained unchanged with orientation. The bubble, it was axisymmetrically placed in the annular liquid film. It had a rounded nose and a rounded tail, and this particular bubble shape was retained while we were trying to change the inclination of the channel. So naturally, for this particular case, as is expected, gravity was played the only role, and as a result, in this particular case, the bubble velocity changed according to gravity, and this is what is explained in this particular curve. Now, since this is something very unique only for a rectangular conduit, I thought that it's worth some discussion and we should be discussing it. And this particular slide, it shows you the Taylor bubble parameters as it shifts from the horizontal to the vertical orientation for the B type orientation. And this is quite expected, because we find that when the channel is kept in this particular way and the orientation changes like this, we find that there are spaces on the two sides of the bubble where it can actually, where the water can flow, and when we make the channel inclined from the vertical, the bubble can move up and it can create an additional channel in the bottom portion through which the water can flow. But when we are moving it up in this particular orientation, we find that the bubble is almost compressed by the side. So, it has very less space to actually move up, and it actually has very less space for gravity to act on it. A similar situation which we encounter for micro channels, where we had said that this is the reason why bubble train flow occurs instead of the dispersed flow pattern, and the buoyancy effects are much less. This we had already said. Well, this is something, see, whatever we have been discussing so long, well, there were lot of things were for mini channels, but initially we had discussed the effect of some unique effect in macro systems. Now, this is a very unique effect which I would like to tell. Now, when we say that surface forces are important in micro channels, naturally the next question which comes, that means wall wettability, wall characteristics, wall roughness should be affecting the flow morphology, and along with that we will be discussing this after I complete my discussions on this particular slide. Along with that, isn't it not very obvious that entry section will also be influencing the flow parameter? Now, not much study has been reported on this. Some people definitely have done, they have used a lot of different inlet sections or the injection nozzles or mixer sections as they are called. Maybe one of them had a concentric or a coaxial type of mixer. Most of the people, they use diametrically opposite, rather a T type mixer is the most common thing. Some people have used a Y type mixer also, but a comparative study, most of the researchers working in micro and mini channels have also mentioned that the fluid does not forget its history, and therefore it is significantly influenced by the entry section. Now, does this not occur for a macro system? Possibly the macro system also is quite influenced by the entry section, but beyond the developing length, the entry section usually has not been observed to influence the flow morphology to a significant extent. But in this particular case, what we were interested in, we just tried to find out that for minor variations in the entry section, really do we have any influence on the flow morphology. So, what we did, we performed some experiments with air and water in downflow for the entire range of mini channels extending from 2 millimeters to 12 millimeters, and we used different angles of the injection nozzle. We in the fluid water air from diametrically opposite points across a T junction, and then we subsequently performed experiments by varying the angle between the two arms. Now, in this particular case, I have just taken up one representative comparison in order to highlight the effect of entry. Let me tell you, this has been shown for a 8 millimeter case. We have obtained identical results starting from 4 millimeters to 12 millimeters. What do we observe? We observe a very interesting phenomenon. For the case of a T junction, suppose both air and water velocities are very low, then in that case what do we find? We find that for low velocities, the water comes here, it is a glass tube. So, naturally water has a natural tendency to wet the pipe wall. It wets the pipe wall and flows as a concentric liquid film with a smooth interface. Usually we have designated this pattern as a falling film flow and annular flow, because for the downflow case what we have postulated is that when the liquid and gas, they are flowing with a smooth interface liquid here, gas is here. We are going to call it as a falling film flow. And now as we increase the gas velocity, we find the surface becomes very wavy, and due to this waviness, liquid droplets are entrapped, or they are entrained in the gas core. And this particular situation, where with the onset of droplet entrainment occurs, we have named this as the annular flow pattern. So from our nomenclature, or rather several people have used this nomenclature, we have distinguished the two types of annular flows, primarily because we found that in falling film and annular, which is marked by the onset of droplet entrainment, the interfacial shear is going to be different. In this particular case, we can neglect tau I as compared to the wall shear stress. But in this particular case, due to the increased waviness, tau I can be comparable with the wall shear stress, and there are additional shears at the liquid droplet portions. So therefore, when we write down the momentum balance equation, which I had mentioned in my first or second class on the introduction of multiphase flow, if you go to that equation, you will find that for falling film flow, just the wall shear stress is sufficient, but while we are trying to model the annular flow, both the shear stresses should be considered. And of course, in this particular case, we can model it in a form of a separated flow model. We will be very briefly touching upon these things in subsequent lectures. We can use a separated flow model where we will write separate momentum equations for the gas core and the liquid film. And in these separate momentum equations, we will just put tau I much less than tau W, and we can model the falling film flow. While for annular flow, we do the same thing. We can write separate momentum equations for A gas core and B, it is not the for A liquid film, and B, it is not the gas core but rather a homogeneous mixture of gas and liquid. So if you compare, in this particular case, I had told you that we are going to write separate momentum equations for the gas core and the liquid film, while in this particular case we shall again do the same approach, but in this case instead of a gas core we have to consider a homogeneous mixture. Now due to this reason, it is very evident that the same equations cannot be applied for low and high phase velocities, or in other words, the onset of droplet entrainment needs to be given special attention while predicting the pressure drop and other hydrodynamic parameters of annular flow. So that is the reason why these two flow patterns have been differentiated and they have been marked by different symbols in the flow pattern map here. Well, again I have digressed from what we were trying to discuss, but anyhow I thought it's important to clarify this particular point, because so long we have just been dealing with bubbly, slug, churn and annular. Suddenly here I have introduced something like the falling film and it might confuse the students that if falling film is annular, then why use a different nomenclature. Now remember one thing, we demarcate flow patterns just because we want to identify areas where one particular set of momentum equations are applicable. Just like in single phase flow, we demarcate laminar and turbulent. Why? In laminar flow, one type of equation is applicable, friction factor equals to 16 by Re for Fanning's friction factor. For turbulent flow, another type of momentum equation is applicable. In this case also, while we would try to creep the nomenclature to the minimum, we would like to differentiate those particular flow regimes where we would want to have separate momentum equations, or in other words, where the morphology influences the hydrodynamics of flow. So anyhow, so now coming back, so we find that for gas liquid downflow, the most natural flow pattern, which is the flow pattern which occurs for very low gas and liquid velocities, is the falling film flow. And as we gradually increase the velocity, if you observe this map, you will find that initially the flow pattern is falling film. As we increase the liquid velocity, naturally for the liquid does, it tends to bridge the gas slugs, and naturally it forms the slug flow pattern. Again we keep on increasing the liquid velocity, the liquid inertia becomes more important, it tends to shear the plugs further into smaller bubbles, and we come across the bubbly flow pattern. But please remember, in this particular case, for this millimeter size channels, we do not get a well dispersed bubbly flow pattern. For this particular case, the bubbles, they are discrete cap shaped, ellipsoidal or disc shaped bubbles with dimensions smaller than the conduit dimensions, but not fully dispersed or emulsified. Well, so now if we come back to our entry section, once we have understood gas liquid downflow through millimeter size channels, we find that at low velocities, in this particular case, we observe falling film flow for quite a good range of velocities. Same experiments with the same diameter tube we have performed for the same flow velocities, just we have changed the injection system. Instead of introducing the two fluids from diametrically opposite points, what we try to do this time is we try to insert them at an angle to each other. And what do we find in this particular case? Just like this case, the water is flowing through this arm and the air is flowing through this arm, but possibly the water, in order to wet this particular arm and fall along this particular channel wall, it needs to climb in the air arm, and since this climbing has to be against gravity, water, it prefers to fall down directly from here. And as a result, what we find is we obtain a unique flow pattern which is not very common in vertical conduits, and this flow pattern is known as the stratified flow pattern, as I have shown in this particular map. So in the stratified flow pattern, what do we get? In this particular case, we have, just like I have explained, this is liquid, this is liquid, this is gas. But in this particular case, just to show you, what do we have through this? Sorry, this is liquid, this is gas. We find that the liquid is flowing along one side and the gas is flowing through the other side. So in this case, this is the liquid portion, this is the gas portion. Okay, both of them are flowing side by side or parallel to each other in downflow, and both of them are in contact with the wall. As a result, in this particular case, there was tau WL there was a tau I which might be negligible and tau wg was equal to 0. In this particular case, we have a tau wl, we have a tau I, we have a tau wg as well. Okay. So, and this is known as the stratified flow pattern. This is known as the this is known as the falling film flow pattern, right. So, therefore, in this particular case, what we find is that when we incline the two entry arms at an angle, we find that we have come across a completely new flow pattern, which definitely is a separated flow pattern, but is different in distribution compared to the falling film case. And in this particular case, both the gas and the liquid, they come in contact with the wall, as a result of which what I have written is we come across 3 types of shear, right. So, therefore, this flow pattern map shows that while falling film exists over a large range for a T junction, there is a considerable portion of this particular area is occupied by the stratified flow. Now, we operate at a higher velocity. What happens? Moment we go to a higher velocity, there is a pinching action of the water, as is evident here, and we find that the gas cannot flow as a single core. On the contrary, the liquid, it tends to pinch the air and break it down into periodic slugs, and the slug flow pattern emerges. And this is evident from the flow pattern map. If you observe, we have obtained slug flow pattern in this particular case. On the other hand, if you observe the Y, we find that the pinching action of the water is not so very sufficient, and therefore, the water, because the water has to climb against gravity and then pierce the air, which is not possible. So, in this particular case, it has just transitioned from the stratified to the falling film flow, and so while it is slug here, it is falling film in this particular case. At still higher velocities, what do we find? We find in this particular case, it is a slug annulus sort of a flow. There is a transition sort of a thing, because the bridging action of the water phase still works, and it tends to break the long gas core periodically, or it bridges the continuous gas core, whereas for the Y junction we find that the flow is more or less annular. So, therefore, with this it is quite evident that entry section does have a remarkable effect, particularly again I should mention that in the mesoscale, and the effect is much more pronounced for lower velocities where inertial forces are less dominant. And in the process we have actually come across a completely different flow pattern, the stratified flow pattern. And here I would like to remind you that when I had introduced multiphase flow to you, I had very categorically mentioned that stratification occurs for horizontal and near horizontal conduits. That is an expected phenomena, because gravity tends to segregate the two phases only for horizontal or near horizontal orientations, and the effect of gravity diminishes as we go to the vertical conduit, and the flow patterns become much more axisymmetric. Very interestingly, for gas liquid downflow in miniaturized systems, in mini channels specifically, we find that it is not only the orientation which is so very interesting, but the effect of entry section was very interesting, and just by manipulating or by designing a proper entry, we could actually attain the stratified configuration which is typical of the horizontal orientation. And this I think should be kept in mind, because this is not a very regular phenomenon, and this is something very unique that we have come across. Now, if you remember a few lectures back, I had told you that, well, we would be concentrating on the mesoscale because the physics of mesoscale is much more interesting and it will interest the students, and through the course of the lectures you have already come to know what are the specialties of the mesoscale and what are the unique features of the operating parameters that you could capture in this particular range. Well, so I end here today, and in the next class again we continue on the effect of geometric and operating parameters, and we discuss the last topic which I wish to cover in this particular series. It is the effect of wall wettability. So let's see what new things we will be encountering in the next lecture. Until then, goodbye.